Are we live streaming these?
Yeah, so I think we should get started now. So let's start recording also in the cloud. So yeah, welcome to the workshop on causal inference meets probabilistic modeling. So usually through the years, we have added a workshop to the summer school, the workshop on the 4th day. And last year, the workshop was on physical inspired Gaussian processes. And due to the interest of the community on Gaussian processes to relate those models to causal inference, we decided this year that we would like to sort of have a set of speakers that have been using probabilistic models in the context of causal inference to sort of talk a bit about their research. So with Javier Gonzalez, we have been also using a bit of Gaussian processes for causal inference, particularly for applications in active learning and in Bayesian optimization. So we are really excited about today's program. So the first speaker that we have today is Professor from October, I believe, Ricardo Silva, who is at University College of London. And Ricardo has a long history of working on causal inference and also probabilistic graphical models. So he's one of the experts in the UK in causal inference, and we're very happy to have him here. So we would also have other speakers from industry talking today, and Amazon and Microsoft, and also members of the university, so academia. I think that's pretty much from me. Do you want to add anything else, Javier?
Yeah, so just to add that we will be following the same format that we had in the summer school. We will be moderating some questions, but there will be a panel discussion at 3:30 today. So if someone doesn't have the chance to you don't have the chance to have your question answered during the talks, there is another chance during the Q&A. So we hope that we could get everyone's questions answered by then.
Okay, so I see we still have 2 minutes. So I think the welcome was shorter than expected. So maybe we just wait for 2 minutes before. Ricardo, you want to share your screen? That's fine. Before Ricardo.
Right. Yeah, and as I mentioned to you before, Mauricio, I need to leave around 10, so I'm afraid I won't be able to stay around after that. But okay, maybe I'll be back to watch some of the talks later on, because the whole program looks extremely interesting.
Okay.
I apologize also not be able to be in the panel, actually. I do have some childcare issues to take care of, so I won't be able to attend the panel.
No problem.
I'm very happy to, whoever wants to contact me offline, very happy to talk to them.
Okay, thank you.
Guys, you can see me now.
Yes, we can see the screen, yeah. Okay, so I think let's start on time. Okay, Ricardo. So Ricardo Silva, maybe for people who just joined us. So Ricardo Silva is going to be a professor now in October, professor and Ricardo at the University College of London, and he's going to start off the workshop. An overview and the role of probabilistic modeling for causal inference. Thank you, Ricardo, for joining us, and up to you now.
Thank you very much for the invitation. Thank you very much, everybody, for joining in. So let me start this whole idea by just giving you 3 types of problems that are related but not quite the same. So I can tell you, for example, I can ask you this question about some person. Let's call this person Mr. X. I want to ask how long this person will live given this person is a smoker, which is a relevant question, for example, if you're pricing life insurance, or if you have some interest in knowing something particular about the individual in terms of what you think is likely going to happen to him or her. Another type of problem is what I showed there in item 2 is you like Mr. X to change his lifestyle. So you may ask yourself, what if I do some change? What if he stops smoking? What's going to happen after that? What is going to be, what kind of difference is going to make? And the third type of question is more in terms of looking back in time and imagining how things would have been different under different course of action. So you may say that Mr. X died of lung cancer. You may ask, well, was this due to the fact that he was a smoker? Would things be different otherwise? These are 3 different types of questions that in one sense use similar data, but they might require very different modeling assumptions. And I'd like to categorize them in three ways in terms of prediction by observation with this first example, just to see any state of the system, predict an outcome. I want to predict under intervention. So it's not only as following a process as business as usual. You interfere with it, and under this interference and this intervention, you like to hypothesize what is going to happen if I do that. The third class is more in terms of explanation. So kind of rewind the clock, so to speak, and try to explain how things would have been different had things been changed. So some of you might be familiar with this popular science book that Pearl wrote, this book of Why. It was out a couple of years ago. This is how Pearl himself likes to categorize causal questions or machine learning questions in general. You have this level 1 that he calls the association level, which is what you usually do in supervised and unsupervised learning, looking at associations and solving prediction problems. The intervention level is when you actually go to the system, changes something. This Mr. X stops smoking, for example. What will happen under that? And the third level is about counterfactuals, things that are contrary to the effect, like things that didn't happen in the past, but like to imagine what would be the effect of it happening. Now, Pearl likes to say that these 3 levels, of course, require extra layers of assumptions. They answer more refined questions from prediction to counterfactual modeling, and that there was a lack in mathematical sciences and AI and statistics on how to formalize these. I mean, to one extent this is true, but of course scientists have been doing experiments for ages, right? I mean, you can ask that fellow Isaac Newton what he did to come up with his conclusions. People running experiments, but as their domains were getting more and more complex, they're getting more noise, they're getting more variability, where probabilistic modeling, for example, to play a role. It would be interesting to put more order in your house. I mean, it's one thing to throw weights from the top of the Tower of Pisa and see what happens. It's another thing to work in a noisy environment where probability plays a bigger role. So that's what motivates statisticians in the early 20th century, people like Fisher and Neyman and Cochrane, people who are looking and understanding causality in a noisier environment. So Fisher, for example, uses motivations from agricultural science. The yield of a crop can have a lot of variability. How can I understand what is a good combination of fertilizers, for instance, that will give me a higher yield? Now, how do you do this when you think about causality? Because causality, in one sense, is understanding change. So what does change mean? How this is related to probability? How is this related to what you usually do in statistics and machine learning? So one way of understanding why things are not that straightforward is using examples that may sound counterintuitive to begin with, but become clear only once you understand some structure about the model, some structure about the system. So in this example that I have there, so say you have a medication seems to be really bad in terms of killing off patients prematurely, those who take it. There are higher mortality rates among those who take it compared among those who don't. So you may think, look at this, you may think, well, it seems clear I don't even need any fancy model. It seems clear this is probably a bad medication, not a good idea to use it. But you know that things are not like that in reality. I mean, because of this issue of confounding, this issue that may have common causes that explain this association. So maybe what happened here is that the medication was prescribed to people who are at higher risk. That physician looked at the patient and said, oh, this patient has no chance, let's try to apply this medication to this individual because otherwise there's no other better alternative. So there's this association between the state of the individual and prescribing the medication. This is a confounding factor. That's why people say the association is not causation, because you may have other explanations why two things are associated that are not causal. So maybe the medication has no effect. The reason why this was associated in the data is because of this common cause on how the physician decides to apply the medication. So if you know these factors, if you know what might be these factors that confound the association, there are all sorts of methods that can throw at this problem and solve it. And this is what the bulk of this talk is going to be about, because the confound is going to be the main issue you worry about in the examples I mentioned here. It's not the only issue, but it's maybe the most important one. And the interest of time, this is what I'm going to focus here, how to cope with confounding. It's particularly hard that are hidden variables. There'll be talks later on, like Nikki Kilbert is a collaborator of mine. We'll go in more details on what to do if we have hidden common causes. But for the most of the talk, I'll look at much more simplified problems that will be hopefully useful to clarify all these notions of causality and probabilistic modeling, the role it plays. Now, as I said, it was the early 20th century, and people tried to start to be more formal about causality, and it was all through this notion of randomized control trial. So you can say you have treatments, you have outcomes, it could be a drug assignment, and it could be a health outcome. And for simplicity, most of the time, I assume I have this treatment X, this variable X, which is binary, and then measure an outcome Y that you'd like to control or like to know what happens in terms of as you change X, how will Y vary? And let's assume I can control X. I can hold the value of X fixed. I can say I can force a patient to take a medication or not. Let's say I can control that. But even under the situation, it doesn't mean I'll be able to disentangle confounding. As you saw, I mean, you can think the physician had the power to decide who takes medication or not. But the data by itself would not tell you what the benefits of the drug were without understanding these confounding factors. So Fisher was really the guy who introduced a way of going around this, the idea of randomization. So you just pick values for X based on something like the coin flip. If you have a coin flip dictating who gets a drug or not, and then that clearly the confound is not there anymore. And that's what the randomized part of it says. Control means I can control X, randomized means the assignment of X is given by something like a random number generator. Okay, and one way that people look into this for a good period of time. Yeah.
Moving to the next slide, I think there is a question that is worth clarifying. So Ineke is asking if the confounding problem is also sometimes referred as the endogeneity problem in the statistics, in case.
Oh yes, it's exactly the same. I think it's a term more common in economics than statistics, but yes, there's a synonym for that.
Thank you.
Yes, so as I mentioned to you, of course, people have been doing causal inference for centuries, right? Newton, Galileo, they're doing causal inference, but not in a very formal way. So that's when mathematical statisticians stepped in. They created languages to express what might be going on. One of the most common ways of doing this is the idea of potential outcome that I'm depicting here. So imagine you have two parallel words that correspond to which treatment you give to people. So this corresponds to variations of my outcome variable Y. I index them as Y naught and Y in this example if the treatment is binary. So when I choose my treatment, I observe what the corresponding outcome was. So here I observe what Y naught was. So this is here the potential outcome under a treatment 0 and potential outcome under treatment 1. If I choose treatment 0, observe that, but this remains unknown. This is missing data. So in one sense, the treatment choice tells you which of these two things I'm going to observe, and the rest is missing data. Now, if you look at the way people do statistical inference based on these models, the classical way is that the randomness is just the flip of the coin. There's no probabilistic model about y. I just assume y is fixed, and the potential outcomes y0 and y1 are also fixed. They are not random variables. Only the choice of treatment is random. So that's extremely simple from the point of view of probabilistic modeling, because it's only about what happens to which word I'm visiting. I'm visiting y0, I'm visiting y1. It's like survey sampling, right? You can imagine that you want to know who will win an election today. You may think that people's minds are made up. All you're doing when you're analyzing the variabilities, who you managed to ask a question on who they're going to vote for and who you didn't manage to ask. So it's the asking that is random, not the quantity that you're thinking about. So that's the classical way of thinking about causal inference. It's still very mainstream statistics today. And the way that people will analyze, even today, it's common to just do a hypothesis testing under assuming that there is no effect. So the null hypothesis would be both potential outcomes are the same. So under that, there is no missing data because the two columns will be equal. So you could get estimates of these averages. You don't observe these guys, but you get estimates of each column here. And under the null, the difference between those would have to be 0. So it could compare estimates between what happens here on average against what happens there on average. And this would be how it would conclude whether something is causing something or not. That's the classical way of doing that. You may think it's a very constrained way of doing this, and no randomness about y, just randomness on x, then doing some hypothesis testing. I mean, of course, it's still very relevant. This is something that people are doing right now when you think about how to test COVID-19 vaccination, right? It's a type of framework they follow. And the reason why I like this is because it uses really minimal assumptions, no probabilistic modeling, just a sampling model for the choice of x. And then under these very minimal assumptions, you can say something on whether a drug is effective or not. And this classical way is kind of very alien to many of us in this workshop, where you think about prediction problems, right? This classical Fisherian way of analyzing causality makes 0 claims of generalization. It really doesn't make any claims about what happens out of sample. Doesn't really look at effect sizes, because if your potential outcomes are fixed, well, do you really care much about what the gap between the averages are? Maybe it doesn't make much sense in this sense. And if you really look at what a classical RCT tells you, it's just some group of people sometime benefited from a treatment. Well, can be more explicit about this, but this is probably not what interests many people here. Many people in machine learning are more interested in control problems or planning problems over time, things that allow you to do some predictions on intervention, right? So the reason why people do RCTs, as I mentioned, is because it's simple, it controls confounding, but they're expensive. There are also some shortcomings on that. Your samples might not be representative, because who knows who volunteers to be part of a randomized controlled trial, right? And sometimes the people who design it might not be looking much in terms of variability. They might be choosing a very specific demographics just to control variability. There's a lot of representativeness shortcomings in a randomized controlled trial, which might not be the case in some domains like web commerce, targeted advertisement, can do much bigger experiments, but even they have practical issues, right? You don't want to search in a very complex space of possible interventions, or even having to make sure that people consent on being experimented with. So this led to the idea of using observational data, which is data that don't control things. Sorry, it may control, but even there might be confounded because you don't randomize it. It's the smoking lung cancer historical case is probably the most famous study, or most famous observation study, because you cannot really experiment with smoking or not. You cannot force people to smoke or not smoke. So there are all sorts of ethical reasons why you might be able to do RCT. And all you have is randomized controlled trials. And when you have an observation study, kind of have the, RCT is randomized controlled trial. Okay, sorry if I didn't make it explicit there. So you cannot do as it is in many cases, or because your data is so limited, you may not be able to answer more precise questions, or like what happens on this particular group of people? How different is the treatment effect for this group of people? And of course, one of the reasons why do placebos instead of just not giving a person a drug is because under lab conditions may be affected by just being told what kind of treatment to do. An observation study is a more natural environment for people to try particular treatments. Now, can I extend this idea of potential outcome that I mentioned to observation studies? That's what one of the most famous lines of work by Don Rubin. This is why it's on the Rubin causal model. Sometimes the name of Rubin causal model, because just the name came up with this idea originally. But if you're coming from our, maybe not everybody's perspective here, but from many people here in this workshop, they probably come from a machine learning AI perspective, which didn't have this baggage of thinking about estimation problems. We have a simple sample, just randomization. It kind of came with maybe overly ambitious goals of control problems, agents roaming around, predicting what to do. So in this case, they create their own languages for that. So for the rest of this talk, I'm going to talk mostly about predicting the effects of interventions, and don't need to think about these potential outcomes or these counter factors. I'm going to switch gears and make sure you understand how one thing moves to another, because both potential outcomes and what I'm going to speak now are very common ways of representing causality. It's good to understand the links between them. But in what I'm going to go now forward is I'm going to abandon this idea of potential outcomes for most of the time, because for the problems that may interest most people here, that kind of entities multiplied without necessity. You don't really need to model all these potential outcomes to understand the effect of an intervention. I mean, there are reasons why those things still be useful. Actually, in this later talk in this afternoon by Nikki, this is work together with the two of us and Matt Kuznets. We kind of use more explicit counterfactual models on that, although that was not really necessary in that case. So the way I'm going to switch here is to think more in terms of adding new types of variables, intervention variables. And I'm going to look at dependencies and independencies between random variables and intervention variables. If you think about the dependencies and independencies, the natural way that I think through them is in terms of graphical models. So you're going to postulate dependence in terms of a graph. But always keep this in mind, that the graph is there just as a syntactic sugar for dependencies and independencies. You're going to see arrows being drawn. These arrows don't only mean something because underneath them are claims about dependency and independence of graphs. So the drawing is not really what makes it causal. It's this idea of intervention variable in relation to random variables. Everything else is just synthetic sugar, so to speak. So what do I mean by this idea of extending a graphical model to introduce intervention variables? So we have these intervention variables are modifications done by some agent. Some agent outside of the system thinks, oh, there's a system here. I'm going to modify this part of it. I'm going to do a shock on it. I'm going to cut things out of it. And this will propagate and could change the distribution of the other variables. So because this is a kind of a different type of event, I want to call that a random variable. It's not a random variable, it's a design variable, an intervention variable. It's something that indexes which type of distribution will follow from that point. So you can think of there's a relationship between intervention variables and random variables, because if you think of something that hasn't been controlled as a random variable, and then somebody suddenly controls it, then it becomes an intervention variable. So you may have things that switch roles from random variable to intervention variable. And that's important that we stress what this means in your notation, that your notation make very clear when something is an intervention, when something is a random variable. So the dual operator view approach is what I'm going to describe in the next slides. It's the most popular formalism, but it's not the only one. Okay. And it's this notion of dependency and independence that is going to explain to us this asymmetry of cause and effect. It's going to follow naturally from making explicit distinction between random variables and intervention variables. Okay, So let's start with the simplest example. There's just a pair X and Y. You're drawing a DAG like that as a directly secret graph where X points to Y. So you know the basics of probability models with DAGs. This implies a factorization, like you see there. First X happens, then Y when X happens. What does intervention mean here? How do I postulate what the intervention is doing to this system? So you think about replacing this random value with a fixed value. So I'm using a different notation here, squares instead of circles, to say this guy here is not a random value anymore, it's just a fixed value. And when I do that, I will assume, this is again by assumption, this is a definition of an operation, that everything else remains the same. Is a modular intervention that changes one aspect of this probabilistic system to replace a random value with a fixed value. And everything else remains invariant. So if you think in terms of this factorization you started with, well, P of X doesn't exist anymore. It's not defined anymore. Just drops out of it, while the other factor remains invariant. So if you think of this as a control value, an intervention value, a design value, whatever you want to call this, this is what the generative story becomes. It's just a story about Y. It's not about X anymore. But I'm going to borrow this function here, there, because under my assumption, the intervention didn't change anything else. And to hammer the point home, I'm not going to refer to X here as just a random variable. This do operation that you see here, which is Euler-Pearl's notation, explicitly says this guy is now an intervention variable set at this little x value that you have there. It's not random anymore. And although this example may look fairly trivial, things can get more interesting when, say, for example, why this is a symmetry between cause and effect. So the corresponding factors of the things you're controlling get erased from your model. So if you think about intervening on Y, well, the factor for X doesn't change, but the factor for Y disappears. So there is no more of this link of X into Y, because my intervention overrid what generated Y. So I'm overriding the system saying, stop here, I'm controlling Y. And graphically can represent like this disconnected graph. So the implication is this, the factor for Y drops down, the factor for X remains. So that's what P of X given to Y would be under this representation. And doesn't matter which little Y I'm choosing here, this doesn't change, the P of X doesn't change. So X is independent of Y in this intervening graph. And that's what the asymmetry comes from. If I control X, Y can vary as I vary X, but not the opposite. If I control Y, the distribution of X will remain always the same. It doesn't matter to which value I fix my Y. That's why I say X causes Y, but not the opposite, according to this model that I postulate in front of you. So everything is operationalized in terms of these independences between my circles and my squares, so to speak. Okay, and this allows you to derive some important ways of connecting causal questions to data in observational studies. And this slide is maybe one of the most important ones in this mini tutorial. So what I'm showing to you here is you postulate a causal structure of the world in terms of a DAG. So by this, you're meaning you are claiming that corresponding interventions will have the corresponding dependencies showing up. So if I intervene on X, if I intervene on X, Z will become independent of the control X, but not Y. So this, if you draw something like this, just you're claiming that you're okay with this. So that's the starting point to postulate the structure. And if you have these structures, then we can see what invariances they imply. And these invariances might tell you, oh, wait, I have something that I could learn from observational data. If I learn these pieces from observational data, I can then maybe plug into the causal question I want to answer, and then have an answer to that, even though I didn't have a randomized control trial. So in this example here, deriving something known in statistics as ignorability. ignorability means to which extent I can treat causation as if it was just association. Well, it depends on our causal assumptions. In our causal assumptions here, say you can start from whatever distribution you have. If they follow this graph, it allows me to read off what P of y given to x is. So as you know, can use the typical rules of marginalization and conditioning, right? So you know that this condition distribution follows from marginalizing z in the original model. But if you have a model given like this, you can apply the same idea. Well, if I just want P of y given to x, I need to marginalize z. But the way I marginalize it is using what the model now postulates under intervention. The model postulates that z is independent of x. So instead of being this particular weighting of my marginalization that would have if you just did condition, if you just did regression, for example, your weighting taking into consideration that you broke this connection between z and x. So this means that if you just want a conditional distribution of y under observing z and under intervening on x, you can apply the same idea. What happens to this model? Well, it's the same thing that the factors of this model transfer to this other one too. So P of y given x and z is the same on the left and on the right. So the graph tells me I can just plug that in. So this do is what I want, what is mathematical equivalent to that. So I'm entitled to use observational data to learn this vector and answer this question, because this allowed me to link the two regimes. So we have a first question here, the Q&A.
Yeah, we have a couple of questions. So Sujog is asking, so just trying to understand this a bit better. I'm working with, imagine that I'm working with extremely rich observational data. How would I say, and how could I plot xy given a versus sy given do a is equal to small a, basically. So how could I visualize the difference between the interventional distribution and the conditional distribution, and why they should be different? I think people try to...
Well, visualizing the difference between P of y given x and P of y given to x can be, they can be very different. It can, for example, if you think about a scatter plot between y and x, it can go in one direction, and while the other goes in the opposite direction. This is possible. Maybe Nikki will show an example of that later on. But in principle, this and that can be very different. I mean, the reason for that is weighting your factors by two different distributions. And these two distributions, P of z and P of z given x, can be very, very different. So, I mean, it can become fairly different, not be completely arbitrarily different, but very, very different. Yeah, y given x and y given to x.
We have another question about the assumption of ignorability and some clarification.
Right. So in statistics, it's common to say I have a treatment x and outcome y, and I have a set of variables z. That makes that implies that this fact that I can drop my do and just condition on x. So then what I'm writing here at the bottom is what people call conditional ignorability. And sometimes in papers, people start from that. They just start by saying, that's true. And then going from there, you start doing inference. So what I mean by deriving ignorability is first you start by writing down the structure of the model. And given the structure of the model, you check whether this holds or not. So it's a more a more basic starting point, so to speak. You start from the causal relationships, and then you ask yourself whether this implies ignorability or not. So I can give an example of this in this slide. So for example, if you postulate there may be some graphs you believe might be responsible for the data, like this left one, the center one, you can check whether conditional ignorability holds on that or not. I'm going to describe a simple criteria very soon. But this graph on the right here, you can also show that conditional ignorability does not hold in general. Again, by graphical criteria, I'm going to exemplify very soon. So instead of starting by saying Z gives me conditional ignorability, the philosophy here is I give you a DAG and let's query the DAG, whether a particular ignorability claims hold or not.
Yeah, I think we don't have any further questions, so you can go ahead.
All right. And you can extend this idea beyond the simple do X operation to have more conditional interventions or contextual interventions. So you can say, for example, that the way you're controlling X may depend on Z. So I think the most elegant ways of doing this is to just add an extra policy variable. I mean, this is actually not uncommon in reinforcement learning, for example. We have these extra nodes describing how actions are chosen. So this node pi is an intervention variable, is a square here. So you may have a special value called the idle value. That means nobody's doing anything external to the system, just running its natural course. So the conditional distribution of X given its parents is just whatever the probabilistic model tell you. Excuse me. But we have this intervention variable taking special values, let's say a particular level of X star. And this means that I'm overriding what Z is doing. I'm just setting extra particular value X star. In general, this could be arbitrary functions. So you could have, this is just some function of Z. So it could be a function of the value that pi takes, and the value that Z takes is the value that X is going to take. And this can be a distribution, doesn't need to be deterministic. And because I like to see interventions always being something external, I always represent them as never having any parents in the DAG. So sometimes in papers you see something like this right-hand diagram. I really don't like that. I mean, I like to think that contextual choices of actions can always be represented in terms of these parentless intervention variables. Okay, so from now on, can always assume these intervention variables never have any parents. And now, once you have this idea that you can kind of link a causal query to a probabilistic model, then we want to think, what's the general idea here? Is there some more general idea by which you can make this kind of transfer learning? In a sense, it's a type of transfer learning, right? You may have observational data. It comes with its own regime, and they want to see, I have this other regime, which is what was the result of controlling something. How can I transfer information from one regime to another regime? This conditional ignorability was a special case. And sometimes we want to ask, when does it hold? When there is some Z that allows me to jump from here to there? When can I make claims like this so I can use what I learn about this factor to predict the effect of an intervention? Now, this is what people call causal identification. You can have ways of transforming this left-hand guy into something like the right-hand side in this equation. It's easier when you have these explicit intervention vertices in this graph to understand how this is done. So this idea of conditional ignorability here can be understood in terms of independencies between the intervention and the outcome. So how can I say graphically whether the Z enforces conditional ignorability? Just have to ask whether this separates pi from y. If you don't know what this is, that's okay, but just think of it as a way of reading off independencies from a graph. So if you don't know what it is, please don't worry, you can check this later, but the main gist is, can I look at this graph from the structure, claim whether my intervention variable and my outcome variable are independent, given X and Z? If they are, great. So I'm entitled to claim this conditional ignorability. So I can entitled to say this is true. And the way this is happening here is if you think about if you condition on X, you know from graphical model that these two guys become dependent. Is a explaining away mechanism. But because I'm conditioned on Z, then this pathway is blocked. So this is true on the left-hand side. This is not true in this example because conditional and X will link this, guys. This is a hidden variable, so this continues to propagate dependencies. This is also being conditioned on, but this is also has parents that become dependent. So you also activate this dependency and then get to reach Y. So this won't be true on the right-hand side. In a situation like this, it's easy to see why I'm entitled to claim conditional ignorability. It's because if I condition on pi equals X, and because I have this independence, I can add X back without any problem, right? X is just redundant. Oops, and from the, sorry, and from the graph here, I know that X blocks my pi, so I can drop my pi and end up with that. And this is how I able to link the interventional and the observational regime. So conditional ignorability is this, there's this question that showed up there. What's the relation between conditional ignorability and conditional independence? Well, this is what conditional ignorability is. Okay, this entitles you to use the right-hand side to answer the left-hand side. Or the right-hand side you can learn from observational data. Conditional independence is what allows me to claim whether this is true or false. Okay, in this example, the left-hand side, this is true. The right-hand side, it is not. And I can read this from the graph. Okay.
Yeah, someone, hi Ricardo. Someone is asking in the chat the relationship between conditional ignorability and conditional independence. But I guess you have already clarified that with these explanations. I don't think we need to repeat.
Okay. So this allows you to come up with ways of calculating other queries. So the one causal query that you're interested in is this unconditional cause effect. So just without conditioning any particular disease, let's say you have a population of people, you want to see the effect of a public policy, which is X. So you want to average over everybody what the distribution of Y is going to be. So how can you do this? I mean, you can apply this formula to get this particular transformation of a causal query into a purely probabilistic query. But in order to apply this, you have to make again, you have to derive again from the graph whether I'm entitled to use this formula or not. This is the most common basic adjustment formula that we see in causal inference. It's basically saying, if I want to know the effect of X on Y, I condition on confounders and I average over the confounders. This is basically what is behind this formula. But to be able to say you're entitled to use it, then you have to look at your graph, and from the graph, you can check if this relationship would hold. And again, there is a graphical criteria for that. It's very similar to conditional ignorability. I mean, you have to check for that independence, just like in the previous slide. You also have to check whether this is not a descendant of X. The variables I'm using to block confounding are descendant of X or not. And oops, sorry, my mouse is a bit fidgety there. I can barely touch it and does something. It's completely alive. And this first guy here basically says, just have to check this extra condition here, because when I do these transformations, again, just conditional marginalization. Everything here is about conditionally marginalizing variables. So if I start from that, what Y is, if I control X by my intervention variable, I can just condition on Z star and average over it. So this would be the averaging weights. But because Z is not a descendant of X, then I can drop pi out of it. And then back to this formula. And that's the entire idea. Just reading off independencies between my pi's and my random variables, that's all. Okay, so I have about 10 minutes left. As I mentioned to Javier and Mauricio, I actually add a lot of things in these slides for people to peruse them and read at their own pace later on. Because I'm making the slides available via the webpage of the workshop. I really didn't mean to go through all of them, but I hope they're going to be useful as extra reading material. So what I wanted to emphasize here is something about how once you have these formulas, how do you actually learn them from data? Because they're not that straightforward. So there's so there are two questions about the slides. I hope Maurice and Javier are going to make them available.
Yeah, so we'll make the slides available for everyone.
Yes, thank you. And the first question is, if you know the causal graph behind observations, the graph plot would require this formula. I mean, the graph, it's not that the graph requires this formula. I mean, it's the graph either implies this formula or not, right? So we don't know whether this here holds or not. You want to check if it holds by looking at the graph. If it holds, then we're entitled to use this formula to get an answer to a causal query. This is how the logic behaves. The graph are the assumptions, and the assumptions will or will not allow you to use particular adjustments of observational data. I hope this makes sense. Okay. So I'd like to spend these last 10 minutes in one particular aspect of causal inferences, how you learn these effects from data. So one possibility here is doing something similar to regression. So one question is, I'm not sure what the correct graph is. Is there a way to test various graphs? You can partially test some graphs. So some graphs will imply particular constraints like independence constraints. So there are ways of falsifying some components of a graph. In general, you cannot fully falsify a graph. That's the whole catch in causal inference. It has to start with assumptions that are not always fully testable with the data at hand. That's what happens in the observational study, right? How do people come to the conclusion whether smoking causes lung cancer? Now, ultimately, they cannot fully test the assumptions. What they can say is, if I look at, for example, one way of on enforcing conditional ignorability, maybe I measure things like genetic factors or behavioral factors or environmental factors. I use them to as my variables that enforce conditional ignorability, and I look whether the answers are approximately the same. So you may have different sets of starting assumptions and see whether they are kind of agreeing with each other. That's one way by which you piece evidence for causality, is by looking at different sources of information. Like twin studies is one source of information for the smoking lung cancer link. But by itself, a single study will have untestable assumptions in it. You may be able to say what is implied by that study that will allow you to look for new data or look for other assumptions to validate what you started with. But by itself, we are going to have some untestable assumptions. It is the entire starting point of a causal model. Because the data is not going to tell you purely causal links. Most of the types is observational, right? So you cannot completely tell you this story. Okay, it all starts with some untestable assumptions. You can do some sensitivity analysis, or you can do some more combinations with other independent studies. Like maybe I should have made clear from the beginning. I always have to have some untestable assumptions. Now, what I'd like to finish with is something that's also direct relevance to people in this workshop in terms of how we actually fit these models to data. So you may think, for example, that if conditional ignorability holds, then you can just do a regression If you just do a regression, you're going to get how y responds to x and z. So what's the big deal here? Oh, the formula saying there's a question here whether this formula is deterministic or not. This formula here is deterministic because the expectation is not a random variable, right? It's just expected value. You could have other ways of expressing the relationship, like a full distribution of y given x and z. But for simplicity, what I'm showing here is just the expected value of y given x and z. It's just a regression function. So the regression function is deterministic. You can model this, for example, with a Gaussian process if you want, and then you can say, well, if conditional ignorability holds, then I don't need to worry about doing anything but a regression, right? So why don't I just do that? What's the big deal in terms of learning the model once I have my assumptions validated? Well, there are all sorts of issues on that. One issue is being aware of a lack of overlap problem. So if you wanted to do a cause effect, it usually means a contrast between two treatment levels. Let's say do x equals 0 and do x equals 1. So I'd like to know this cause effect, which is known as the average treatment effect, which is a contrast between two levels of the treatment. Now I could fit a regression to the first guy, fit a regression to the second guy, and take the difference. This is a valid way of doing that. But it doesn't mean I'm going to be able to do this, because you may be doing a wide extrapolation of one of these guys. So one of these might be a very terrible estimate of the quantity you want to fit. And to understand this, remember that in an observation study, your treatment X and your variable Z are associated. So particular combinations of X and Z might not be anywhere close to your data. This example here, you have just one covariate Z, you have one variable Y, and then you have two treatment levels, X equals 0 and X equals 1. So under X equals 0, if I control X to be 0, this is how the expected value of Y would change as a function of Z. Likewise, if I fix my X to 1, I'm controlling X to be 1, this is how the expected value of Y would change as I vary Z. Because X and Z are associated, you may have something like what the data points show to you there. Sorry, what they show to you there, that only in this region here, you have both X equals 0 and X equals 1 showing up for a particular value of Z. If I'm, let's say at Z equals 10, so I'd like to know the cause effect, the average treatment effect will be this gap, how Y varies in expectation when I vary X from 0 to 1. So the cause effect will be this gap. But here I have no data for X equals 1. So the implication is this first guy here, I would have a very bad estimate under a particular level of Z. So when you're doing regression methods for finding cause effects, you need to be aware of these issues. In a naive regression model is not particularly great. That's why people come up with variations of it. So just to give you an idea what kind of variations people use, one variation is to parameterize the model like this. So you have a baseline response, and we have the cause effect. So when X varies from 0 to 1, so when X goes from 0 to 1, you have these other functions being the cause effect. So the advantage of that, this way of representing your causal model, is that you can have very smooth regularization, very smooth priors for the cause effect, even if this regression is very wild. You could have a very wild regression function, right? If you change just X from 0 to 1, maybe the gap is not great. The gap maybe is modest. Maybe it varies very smoothly with Z. And this parameterization tells you that. This parameterization allows you to put maybe a less regularization on the baseline response and make the cause effect very smooth, maybe even linear. Okay, so all these issues that people have to take into account, considering that just naive regression might not be good enough. So naive regression may kill you because you may have a lot of parameters that you don't care in a regression equation. So even if the model is linear like this, if you have a very simple model where you have the treatment X and you have a lot of covariates Z, in the model like this, all you care really is this coefficient alpha. And this coefficient alpha is only defined, of course, because there are also these beta coefficients here. So you need to fit a model that includes alpha and beta. And if you have a lot of these, you may want to regularize that, and maybe we want to use a Bayesian approach for that, put a prior on alpha and beta. But in general, this might really hurt you. I mean, this is bias variance trade-off, right? You want to regularize alpha and beta to have a better bias variance trade-off. So on average, over all your parameters, you're doing okay. But you don't care about beta here. If you want to know whether x0 is better than x1, for example, all you care is about this coefficient alpha. You don't care about beta. So we regularize everything. You're going to introduce a lot of bias because that's what regularization does, right? Regularization adds bias. And they're going to get this to be very poorly estimated. Okay, if you get this, if you just do a naive Bayesian regression here, you can show that if this is high dimension, Z is high dimension, you're going to do a poor job. You want to do a poor job because that's not, you're answering a general question on how to model Y given X and Z, while the question that you care is just, what is this coefficient alpha? Everything here is what a statistician calls a nuisance parameter. Betas are nuisances. You don't care about them for deciding which treatment is better. You only care about alpha. And there are better ways of doing this that tackle the problem more directly. You can still do some sort of Bayesian approach for that, but you have to be clever on how you parameterize your model. That's one of the messages I want to tell you here. It's just not a matter of getting, let us say, a Gaussian process and blindly trying the crank of what we typically do for supervised learning, and then spitting out a regression model, because it's going to be suboptimal. Because this answers a more general question than what's important for causal inference, which might be just the causal effect, just the alpha that you see in this example. So somebody asked for references. Actually, my slides have several references. This phenomenon for the linear model, for example, is very nicely explained in this paper. It can be a bit surprising. If you never look at causal inference, you may be surprised to think it looks like regression under some assumptions, but it's not, because you may have more specific questions. And the bias variance trade-off that you have for prediction, that you have for supervised learning, is not the same bias variance trade-off that you have for more focused causal question. You may have a lot what is being traded off in terms of bias variance. It's just going to hurt you in terms of what you really care, which might be just a single parameter. It might be just a drop in the bucket of one gigantic model. So I do recommend that, I mean, this paper is actually, a paper like this is actually very highly accessible. I really recommend it for this audience here to get first grasp on the issues are. It's not just a dumb turning of the crank for Bayesian inference. You really have to think a bit how you represent your model. And hopefully something like this is going to be useful. So there are other references that I added here that look into the more complex case with nonlinear models. So this is a very non-Bayesian way of doing this. Maybe it's worthwhile you read about it on why this is sometimes a likelihood function can hurt you, because it forces you to think in terms of a lot of nuisance parameters. So you may want to do a non-standard way of fitting data that is not just regularized maximum likelihood. And what implications this has to Bayesian inference is still a bit unclear in this context, but you can start to look into it by references like that, which you'll be able to find in my slides. Okay. So to conclude,
sorry, Ricardo, I think we are at time. Thank you very much for the reference. I don't know if there is anything that you want to add, but maybe we should be wrapping up the talk. So
no, not really. There are many other things I didn't cover here, but I leave some reference. For example, if you have more than one treatment, this is a sequential problem. There's links to that to reinforcement learning. And I guess other talks later on to cover topics I didn't even try to cover here. So keep that in mind. And this is basically the main message I want to say. There's a lot of stuff out there, and this is just dipping your toes in it.
Thank you very much for the talk and for all the material that you have put together in the slide. That I'm sure will be very useful for the audience of the workshop. I'm keen to review the material myself and to see what else did you have in mind and you couldn't talk about. So thank you very much on behalf of all the audience and the organizers of the workshop. So I think we have now 25 minutes break, right, Mauricio?
Yeah, thank you, Ricardo, for the very interesting tutorial and for all the references. Yes, so we have 24 minutes. We'll be back with the second talk at 10:30.
Yeah.
All right, I need to run out to my next meeting.
Yeah,
so
thank you for your time.
It was a pleasure.
Bye.
Okay. Bye.